Swayam Prabha. Digital India. Educated India.
Welcome to Lecture 15 of Computer-Aided Engineering Design. Here, we'll discuss how to design Bezier segments and curves. In the layout, we are down the ladder. We are just done discussing how to design Ferguson segments and composite Ferguson curves. Now, we are discussing Bezier segments and curves. Why is there a need for other curve design models? In previous lectures, we had discussed how to design Ferguson segments and curves. It was not very intuitive to specify the slope information or tangent information. This is especially when our designer wants to design a three-dimensional composite curve. Our designer is more comfortable in specifying the data points as opposed to higher order information like slope or curvature. We are looking for alternative curve design methods that allow to specify only design points or data points while maintaining local shape control. Let's look first at the graphic construction of a parabola. All of you must have done this in your first year engineering drawing course. Given two line segments, how to construct a parabola using them. The key idea is this. You divide the two line segments such that the ratio of this length over this length is the same as the ratio of this length over this length. And then join these 2 points. You repeat the procedure again. Here, this length over this length is the same as this length over this length. Once again, this length over this length is the same as this length over this length. You would keep continuing the process and finally you would want to draw a curve that passes through this point, through this point, and is tangent to all these line segments. The curve in red is your parabola. The construction in the previous slide alludes to the three tangent theorem to construct a parabola. We have two segments. We discretize them such that the length of this segment over the length of this segment is the same as the length of this segment over the length of this segment. We join these 2 points and we mark another point on the segment maintaining the length ratio. We have seen before that the curve joining this point, and this point is a parabola. To add further, this curve is also such that these three line segments are tangent to it. Let's nomenclate different points now. Point A, point B, C, D, E, and F. For F to lie on a parabola and line segments AB and BC and DE to be tangents to the curve, as per the theorem, these length ratios, that is AD over DB, should be equal to BE over EC, and that should be equal to DF over FE. We have seen this relation before. Any point on a line segment can be expressed as D equals 1 minus U times A plus U times B, where U is a parameter that assumes the value between 0 and 1. A and B are the position vectors, and D is the position vector of a point on the line AB. For U equals 0, D would merge with A, and for U equals 1, D would coincide with B. Likewise, point E on the segment BC is given as 1 minus U times B plus U times C. Notice how the length ratios are being maintained. The value for parameter U would be identical in these two relations. And finally, F as 1 minus U times D plus U times E. Again, the length ratios are maintained. If we substitute for D from here and for E from here, we will get F equals 1 minus U squared times A plus 2U times 1 minus U times B plus U squared times C. Once again, A, B, and C are position vectors of these 3 points. It would not be very difficult for us to figure, using coordinate geometry, that F would lie on a parabola. This may be one way to verify how point F would lie on a parabola. The generic equation of a conic is given by ax squared plus 2hxy plus by squared plus 2fx plus 2gy plus c equals 0. Here, a, h, b, f, g, and c are unknown constants. We have seen from the construction before that the parametric equation of a parabola is given by f equals 1 minus u squared times a plus 2u times 1 minus u times b plus u squared times c. One can extract the x component of f and the y component of f and substitute those conditions over here to determine these unknown constants. And then one could verify for a parabola that h squared equals ab. Let this be an exercise for you. The de Castelnu's approach generalizes the construction. One may not constrain himself or herself to only 2 segments to start with. One would notice that a parabola is a result of 2 linear interpolations. A generalization that de Castelnau worked on was based on repeated linear interpolation. Let's see this graphically. Assume that we have this control polyline, as we call it, a set of line segments adjacent to each other. Let's nomenclate the points. This point here is B sub 0, super 0. I'll explain what the subscripts and superscripts mean in a while. This point B sub 1, super 0, B sub 2, 0, B sub 3, 0, and B sub 4, 0 for this example. The subscript here represents the index of these endpoints, and the superscript represents the stage of linear interpolation. At this time, we have not performed any linear interpolation as such, and therefore these numbers, the superscripts, are 0. Let's now start performing the first stage linear interpolation. For a given value of parameter u, this length ratio is specified. I can mark this point as B01. This 1 now represents the first stage linear interpolation. This is the first point that I have marked, 0. Take 2. I maintain the length ratios and keep marking the points. This point here is B sub 1, super 1. This point here is B sub 2, super 1. And this is B sub 3, super 1. I join these points to these line segments, and I do not stop. I keep performing linear interpolation. This point here on this line segment represents the first point of stage 2 linear interpolation. That's why it is nomenclated as B sub 0, 2. Notice that I'm maintaining the length ratios throughout my linear interpolations. The point on the second segment is B 1, 2. The point here is B 2, 2. We join these 3 points and continue with linear interpolation. This point here is B sub 0, 3, representing the first point of stage 3 linear interpolation. This point here is B sub 1, 3. And finally, we join these 2 points. We mark a point here on this line segment, and we nomenclate this point as the first point of the fourth stage linear interpolation. You would realize that we can go no further with linear interpolation anymore. This curve here would be very similar to a parabola that we have seen before, and this curve will pass through the first point, the last point, and the final point as a result of repeated linear interpolation. Also, the first line segment, the last line segment, and this line segment over here, they all will be tangent to it. Very similar to what we had seen in case of parabola. Now let's try to work backwards. We start from B04. It is the result of linear interpolation between B03 and B13. For a given parameter u, it is 1 minus u times B03 plus u times B13. B03 itself is a result of linear interpolation between B02 and B12. We know what the relation is. We directly substitute the result for B03 and likewise for B13 as well, realizing that B13 right here is a result of linear interpolation between B12 and B22. You would get the final expression as 1 minus u times 1 minus u B02 plus u times B12 plus u times 1 minus u times B12 plus u times B22. All you will need to do is keep on substituting for these points here, which we call the intermediate decassager points. If you keep on working, the final result will look like this. The left-hand side, which represents a point on the curve for a given value of u, is B04 equals 1 minus u raised to 4 times b sub 0 super 0 plus 4 times u times 1 minus u cube times b10 plus 6 u squared times 1 minus u squared b20 plus 4 u cube times 1 minus u times b30 plus u raised to 4 times b40. Notice that this expression here is of degree 4 in u. This superscript, therefore, represents the degree of the curve. Also note that B00, B10, B20, B30, and B40 are design points that are specified maybe interactively by the designer. Beazier's approach was not geometric. It was algebraic. In general, a point on an nth degree curve can be written as summation I going from 0 to n combination I times 1 minus u raised to n minus I times u raised to I times bi. Bi are the design points specified by the designer. This is equal to summation I going from 0 to n b sub I super n as a function of u times bi. If we relate bi to the nomenclature that we have seen before, bi would be the first stage design points, bi 0, and capital B sub I super n would be functions of u. That will be equal to n combination I times 1 minus u raised to n minus I times ui. This is the term right here. Capital B sub I super n are called Bernstein polynomials. As I said before, de Casteljew's approach was geometric, while Beazier's approach was algebraic, and it followed the de Casteljew's approach. It is interesting to note that both the approaches gave the same result. If you look at this expression, b sub 0 super n equals I going from 1 to n within summation, capital Bi super n, a function of u, times Bi, the design points. This expression represents a Bezier curve, a degree n. And in fact, both the Bezier's approach and the de Castelnu's approach give the same Bezier segment. Coming back to de Castelnu's approach, there is a very nice triangular scheme to compute the intermediate de Castelnu points. Let's see how. The first thing we need to do is arrange all the design points in the first column. B00, B10, B20. We keep on going. B n minus 20, B sub n minus 1 super 0, and B n 0. In the second column, we start placing the first stage interpolation points. We use this point here, B00 and B10, combine them to get B01. Likewise, we use B sub 1 super 0 and B sub 2 super 0, combine them together and get the first stage linear interpolation between them. This linear interpolation is being performed for a known value of u. We keep on going. We combine adjacent design points to get a new point. In this case, B n minus 2, 1. And finally, we combine the last two design points to get B sub n minus 1 super 1. The third column would have all intermediate de Castelnu points as a result of the linear interpolation between points in the first column. For example, we combine B01 and B11 to get, you guessed it right, B02. Likewise, we combine Bn minus 2 super 1 and Bn minus 1 super 1 to get, once again, you're right, B n minus 2 super 2. We keep on following the scheme until we see the last 2 points in the last but one stage of linear interpolation as B0 super n minus 1 and B1 super n minus 1. And finally, we combine these two to get our B sub 0 super n. Notice once again that this point will lie on an nth degree curve in the parameter u. The arrows pointing downwards represent multiplication with factor 1 minus u, and those pointing upwards represent multiplication by u. There is a point I want to mention here. This column, the very first column, contains the position vectors of all the design points. By that I mean that in this entire triangular scheme, we are working individually with the x coordinates, with the y coordinates, and with the z coordinates. These points here on the second column, on the third column, and so on and so forth would be again the position vectors of all the intermediate de Castelnu points. one would keep that in mind. Let's now discuss some properties of Bunstein polynomials. First one, non-negativity. For parameter values between 0 and 1, all Bunstein polynomials, capital B sub I super n, are non-negative. Well, we know that Bunstein polynomials are given by n combination I times u raised to I times 1 minus u raised to n minus I. We can expand n combination I in terms of n factorial over I factorial times n minus I factorial. Notice that for u to lie between 0 and 1, this is positive and this is positive. So there is no way in which these Bunstein polynomials will be negative. Let's look at a few examples. These are the Bunstein polynomials for a degree 3 Bezier curve. This is b sub 0 super 3. This one is b sub 1 super 3. This one is b sub 2 super 3. And this is b sub 3 super 3. You would notice that they are all non-negative. Another example of degree 4 Bunstein polynomials. This one is b sub 0 super 4. This one here is b sub 1 super 4. This is b sub 2 super 4. This one is b sub 3 super 4. And finally, this one is b sub 4 super 4. Once again, all of them non-negative. The second property of Bunstein polynomials. This one relates to the partition of unity. All Bunstein polynomials will sum to 1. This is interesting. You start with 1 and you add to it minus u and plus u. The result is expected 1. What you do now is raise it by an exponent n. As you would know, again, the left-hand side will be 1, but the right-hand side can be expressed as a binomial expansion of 1 minus u plus u raised to n. This is how it looks. N combination 0 times 1 minus u raised to n times u raised to 0 plus n combination 1 times 1 minus u raised to n minus 1 times u plus n combination 2 1 minus u raised to n minus 2 times u squared, and many terms. This would be the last term here. N combination n times 1 minus u raised to 0 times u raised to n. If you notice, the right-hand side will have terms that would individually correspond to Bunstein polynomials. For example, this term here would represent the first Bunstein polynomial of degree n. This term here would be the second Bunstein polynomial, again of degree n. And the last one here will be capital B sub n super n. While the left-hand side would still be 1. We have exactly shown this relation here. Once again, all Bernstein polynomials of the same degree would add to 1. And this is partition of unity property. Next, Bernstein polynomials as barycentric coordinates. I'll tell you what barycentric means in a while. Non-negativity and partition of unity properties make Bernstein polynomials barycentric coordinates. The term barycenter refers to the center of gravity. Let's say we have a set of points x1, x2, x3, x4, x5, x6, and x7. If there are masses associated with these points, for example, m1, m2, m3, m4, m5, m6, and m7, it is possible for us to compute the center of mass of these points. That would be somewhere shown by the red dot over here, xcm, the coordinate of the center of mass. We also know via geometry that this center of mass would lie within the convex hull defined by these points. So the red dot will never be outside this convex polygon here. To re-emphasize, xcm will always lie within the convex hull of data points. This expression is very familiar. The coordinates of the center of mass would be given by m1 x1 plus m2 x2 plus m7 x7 over the sum of all the 7 masses for this example. Here x would either be the x coordinate or the y coordinate. If we replace all these masses by Bernstein polynomials, we have x as a function of u now, because all these Bernstein polynomials are functions of u respectively. If we replace m1 by, say, b sub 0 n, m2 by, say, b sub 1 n, and so on and so forth, we get xu as b sub 0 n times x0 plus b sub 1 n times x1, and so on and so forth, up till b sub n super n times xn over the sum of all Bernstein polynomials. We have seen, using the partition of unity property, that all these Bernstein polynomials will sum to 1. And therefore, this expression here will represent a point on the Bezier curve. What am I trying to say here? Well, for a given value of u between 0 and 1, x of u will always be seen to be within the convex hull of data points, no matter what u is. In other words, a Bezier curve will always lie within the convex hull of data points. And that is something that we'll see later. This is just for you to keep in mind as of now. The third property of Bernstein polynomials, symmetry. Capital B sub I super n is the same as capital B sub n minus I super n as a function of 1 minus u. We start with the left hand side. B sub I super n is given by n combination I, 1 minus u raised to n minus I times u raised to I, and we expand n combination I over here. This expression is equal to factorial n over factorial p times factorial n minus p times t raised to p times 1 minus t raised to n minus p. If we replace 1 minus u with t and n minus I with p here. This expression further becomes n combination p times 1 minus t raised to n minus p times t raised to p, which is in fact the pth Bernstein polynomial of degree n. And if we replace p here and t here, we get b sub n minus I super n 1 minus u, which is the right hand side here. The fourth property, recursion. d sub I super n as a function of u is equal to 1 minus u times b sub I super n minus 1, a function of u, plus u times b sub I minus 1 super n minus 1 u. What do I mean here? The ith Bernstein polynomial of degree n can be expressed as a linear combination of the ith Bernstein polynomial of degree n minus 1 and I minus 1th Bernstein polynomial, again of degree n minus 1, with the weight factors 1 minus u and u here. To prove this, let's start with the right hand side. 1 minus u times bi super n minus 1 plus u times b I minus 1 super n minus 1. Let's expand these Bernstein polynomials to get n minus 1 factorial over factorial I factorial n minus I minus 1 times 1 minus u raised to n minus I times ui plus n minus 1 factorial over I minus 1 factorial times n minus I factorial times 1 minus u raised to n minus I ui. Notice that these two terms are absorbed in this expression. If we work further with the right hand side, what we can do is we can take this factor out common, which is n minus 1 factorial over I minus 1 factorial n minus 1 minus I factorial 1 minus u raised to n minus I times ui, and what will be left with will be 1 over I plus 1 over n minus I. A little bit of algebra. This term here will be n over I over n minus I. This n minus I term gets absorbed over here to get n minus I factorial. This I gets absorbed over here to get I factorial, and n times n minus 1 factorial is n factorial. And we have this term right here, 1 minus u raised to n minus I times ui. And this is the ith Bernstein polynomial of degree n, which is the left hand side. Let's look at some derivatives of Bernstein polynomials. We'll be needing these derivatives later to design composite Bezier curves, to impose slope and curvature continuity conditions at junction points between individual Bezier segments. We already know how Bernstein polynomials are expressed as functions of u. The first derivative of an nth degree Bernstein polynomial is given by b sub I minus 1 super n minus 1 minus b sub I super n minus 1. Here we follow a convention. B sub n minus 1 sub minus 1 is equal to 0, and b sub n minus 1 sub n is equal to 0. Notice that I am using a slightly different convention for Bernstein polynomials over here. The first term here represents the degree, which is the same if I represent the degree by the superscript here. Many books tend to follow this notation. We know what a Bernstein polynomial is of degree n. It is n factorial over factorial I factorial n minus I times 1 minus u raised to n minus I times u raised to I. Differentiate this with respect to u to give factorial n over factorial I factorial n minus I. This is n minus I times 1 minus u raised to n minus I minus 1, and there would be a negative sign over here if we differentiate this term here with respect to u, plus I times 1 minus u raised to n minus I u raised to I minus 1. We absorb this term inside to get factorial n over factorial I times n minus 1 minus I factorial times 1 minus u raised to n minus I minus 1 u raised to I plus factorial n over factorial I minus 1 times factorial n minus I multiplied by 1 minus u raised to I minus 1. A little bit of work will lead us to common factor n that multiplies n minus 1 combination I minus 1 times 1 minus u times u raised to I minus 1 minus n minus 1 combination I 1 minus u raised to n minus I minus 1 times u raised to I. And this is the I minus 1th Bernstein polynomial of degree n minus 1 minus the ith Bernstein polynomial of degree n minus 1, which is the same expression over here. Likewise, the second, the third, and the fourth derivatives can also be computed. Now let's discuss barycentric coordinates and affine transformation. Bernstein polynomials allow description of a curve to be space independent of the coordinate frame, and we'll see how this happens using a simple two-dimensional example. First, what is an affine map? An affine map is of the type y equals ax plus t. X would be the Cartesian vector of a point, A is the transformation matrix, and T is the translation vector. Y is the Cartesian vector of the result. We have seen before that if we use homogeneous coordinates for x and y, this translation vector gets absorbed in the 4x4 transformation matrix. Anyhow, let's first investigate how axis rotation will affect the relations. We have a two-dimensional Cartesian space. We have a point A, another point B, and a point C, which is represented as a weighted linear combination of points A and B. Here the weights are scalars lambda and mu. If we rotate the axis to x prime, y prime, maintaining the position of the origin, and if the rotation angle is theta, what happens? Well, A prime, this point here, will now be expressed in terms of new coordinates x1 prime and y1 prime as a two-dimensional rotation matrix with terms cosine of theta, sine of theta, minus sine of theta, cosine of theta, times the original position of A, given by coordinates x1 and y1. Likewise, the new coordinates of B will be given by x2 prime, y2 prime, which is equal to the same rotation matrix here, pre-multiplying the original coordinates of B, given by x2 and y2. If we maintain this linear combination, C prime star will have the x coordinate as lambda times x1 prime plus mu times x2 prime, and the y coordinate will be lambda times y1 prime plus mu times y2 prime. In matrix form, this will be lambda times the column vector x1 prime y1 prime plus mu times the column vector x2 prime y2 prime. Try to relate this expression with this expression here. If I substitute for x1 prime, x2 prime, y1 prime, and y2 prime, the right hand side would become lambda times this rotation matrix times the original coordinates of A plus mu times the rotation matrix times the original coordinates of B. I can take the rotation matrix common, and I'll have lambda times x1 y1 plus mu times x2 y2, which is nothing but C. So we observe that the coordinates of C1 prime star is the same as the coordinates of. In other words, the rotation of the axes does not affect the linear combination here. Now, let's study the effect of axis translation by a vector PQ. We have the original axis, point A, point B, and point C. Let's translate this axis by vector PQ. The new coordinates of A with respect to this translated axis will be given by A prime, which is x1 prime, y1 prime, which is equal to x1 minus p, y1 minus q. The x coordinate of B prime will be given by x2 minus b, and the y coordinate of B prime will be given by y2 minus q. If we maintain the same linear combination, we'll have C prime star equals lambda times A prime plus mu times B prime, while C prime will be given by lambda times x1 plus mu times x2 minus of p. This is the x coordinate, and the y coordinate will be lambda times y1 plus mu times y2 minus q. How did I get this expression? Well, note that C was expressed initially as a linear combination between A and B. And this translation of axes would directly affect that relation. Let's further see if C prime star is the same as C prime. We start with C prime star. We substitute the coordinates of x1 prime, y1 prime, and x2 prime, y2 prime from here. We get C prime star equals lambda times x1 minus p, y1 minus q, plus mu times x2 minus p, y2 minus q. The x coordinate of C prime star is lambda times x1 plus mu times x2 minus of lambda plus mu times p, and the y coordinate is lambda times y1 plus mu times y2 minus lambda plus mu times q. What I have done here is I have added and subtracted p from the x coordinate, and likewise I have added and subtracted q from the y coordinate. In fact, these two expressions are respectively the same as these two expressions. Now, if C was to be expressed in the new, that is translated coordinate system, we should have expected the coordinates of C prime to be identical to those of C prime star. This would mean that this expression should be the same as this expression, and the y coordinate of C prime should be the same as the y coordinate of C prime star. And this can happen only when the two scalars sum to 1. Notice that we never mentioned that lambda and mu cannot be negative, or 0 for that matter. All we see here is the two scalars, they should sum to 1. Affine combination is a type of linear combination where the respective weights sum to unity. As I mentioned before, these weights need not be all positive. An affine transformation is a function that maps straight lines to straight lines. It preserves parallel lines and overall preserves all affine combinations, just as a linear transformation would preserve all linear combinations.